Hi everybody, I'm Africa, a Maria Sklodowska-Curie researcher and in-house cell biologist at Biogelx. Today, I'm going to put in context my project and explain why our technology is relevant for its development. Additionally, I'm going to specifically talk about my research objectives and show you some of my preliminary results. As you may know, 2D cell cultures are not representative of cells residing in their complex microenvironment, and 3D offers a better alternative to represent in vivo behavior. However, adoption of 3D systems in the drug discovery industry has been hampered by challenges in standardization and analysis. That's where synthetic peptide hydrogels play a role. Biogelx synthetic hydrogels offer a 3D cell culture matrix that is simple, reproducible, and can be tuned to meet the requirements of any cell type. And what does it mean that they are tunables, that the gels are tunable? The stiffness of our gels can be easily modulated to mimic a broad range of tissue types, from 0.5 to 100 kilopascals. We have tried it previously for the development of brain and bone tissue. The biochemical composition of our gels can be tuned as well, allowing the incorporation of biomimetic sequences of key extracellular matrix proteins such as fibronectin, laminin, and collagen. The core technology of our products consists of self-assembly short peptide amphifiers. They contain structural fiber-forming components, and that's what we call the gelator peptide, and functional components, what we call the surfactant peptide, and these are F-MOC-diphenylalanine and F-MOC-serine respectively. The surfactant peptide introduces biochemical functionality to the surface of our scaffolds, making it suitable for cell adhesion. Importantly, the scaffold provides the same nanoscale matrix structure as human tissue. We supply our products as lyophilized powders. Rehydration with water achieves a free-flowing pre-gel solution. The fibers form the hydrogel when they come in contact with the calcium ions present in the culture media. Calcium acts as a cross-linker, locking the fibers in place to create a 3D scaffold. So yes, definitely in our specific case, calcium is the gelator. Our gels, here it is where my project comes, are currently utilized to help in the development of an innovative bio-orthogonal catalytic approach to cancer treatment. This involves customizing hydrogels capable of mimicking cancerous tissue and developing in vitro 3D cancer models as drug testing platforms. Eventually, I will be also providing insight into our hydrogels to act as drug nanocarriers themselves. Firstly, I am focusing on characterizing the most appropriate hydrogel for mimicking cancerous tissue. The breast cancer cell line MCF7 was selected to customize Biogelx hydrogel parameters, initially focusing on functionalization, stiffness, and cell density. Cellular features such as viability, growth, and correct morphology are evidenced through live-dead assays, F-actin fluorescence imaging, and alarmar blue. Evidence of correct cellular functionality will be also provided. Noticeably, Biogelx scaffolds can be used for an initial 2D seeding method or mixing both pre-gel and cells at the same time to achieve an accurate 3D tissue model. At the beginning, I characterized parameters of cells seeded on 2D. Currently, I'm applying the information gathered to the creation of the 3D breast cancer tumor model. Then, I might want to develop more advanced tumor models combining different cell types such as MCF7s and cancer-associated fibroblasts, or even utilize HUVEC to create an angiogenesis model. I would also like to extend my work to the MDA MB231 breast cancer cell line that has been shown to be highly invasive and will provide further evidence for the assessment of the new developed bio-orthogonal chemotherapies. I'll also provide insight into hydrogels as drug nanocarriers cells, as I said before. Lastly, an in vitro 3D drug assessment with the generated models will take place. Through extensive live imaging, I have evidenced the viability, clustering, and correct cell morphology of MCF7s seated on Biogelx RGD hydrogels at early time points, and these were 1 to 3 days in culture. This was shown at low cell densities, in particular 2.5 per 10 to 4 cells per square centimeter, seated on low to medium stiffness hydrogels. And these are 0.8 to 1.1 kilopascals hydrogels and 3 to 4 kilopascals hydrogels respectively. Intriguingly, normal and non-invasive stroma of breast cancer patients was shown to be predominantly of 0.4 kilopascals. And this is actually quite interesting according to the results we just obtained. The results were also corroborated at higher cell densities, 4 per 10 to 4 cells per square centimeter, 1.6 per 10 to 5 cells per square centimeter, and 5 per 10 to 5 cells per square centimeter. And this last one, 1 million cells per square centimeter. As you can see, cell viability as well as clustering and correct cell morphology is evidenced on the top of Biogelx RGD hydrogels at the previously chosen stiffness ranges. These were 0.8 to 1.1 kilopascals and 3 to 4 kilopascals, as I said before. These images that I'm showing you right now were taken on day 1, but the same features were also proven in 3-day cultures. What I want to do next is evidencing cell functionalities through quantitative techniques. These are qPCR and Western blot. I also want to extend the research to a comparable healthy breast tissue model, and in the case of MCF7, this will be the MCF10A cell line. Lastly, I will use the created models to test the effectiveness of traditional and newly developed chemotherapies, comparing the outputs of this research to those of conventional cancer models. Finally, I want to remark that further replicates and time points are needed to understand the presented results within the framework of cancer biology. So, in conclusion, these results provided evidence for viability, clustering, and correct morphology of MCF7s initially seated on Biogelx RGD biofunctionalized hydrogels at early time points. This has been shown at low to high cell densities and low to medium stiffness gels. So thank you very much for your attention, and last but not least, I would like to gratefully acknowledge the laboratory of Professor Matthew Delvey at the University of Glasgow for helpful discussions and cell culture support.